Okay, so welcome to this second video on the exponential distribution. So the first thing we're going to discuss is similar to in the case of the general normal distribution, there was a standard normal distribution. In the same way, there is a standard exponential distribution. So standard exponential distribution is the first thing we're going to discuss. Standard exponential distribution. Okay, so this is the exponential distribution. So if you have some random variable, again you have your abstract probability space here being mapped onto your positive real numbers, so your interval 0 to plus infinity. And if x is distributed standard exponentially, then it means that it's exponential with parameter 1. So if we look at the PDF of the standard exponential distribution, then it's going to be little f of x is going to be equal to e to the negative x, where lambda is equal to 1. So the general exponential distribution, the PDF is equal to lambda e to the negative lambda of x, whereas in the case of the standard exponential distribution, the parameter is equal to 1. And just in the case, just as in the case of the general normal distribution, where basically a general exponential, well, a general normal distribution, if you remember. So we called the general normal distribution y, and we found that it was equal to sigma times x plus mu of a, where x was a random variable distributed standard normally. So basically, if you have a random variable mapping an abstract probability space onto the standard normal distribution, there will exist, you can easily construct another random variable y, which is just sigma times x plus mu. So basically, just take every real number in here, multiply it by sigma and add mu, and then that will be generally normally distributed, or have general normal distribution with mean mu and standard deviation, variance sigma squared. So just as in that case, we can multiply this by something to turn it into a general normal general exponential distribution. So we're going to turn the map, and we're going to map it onto other real numbers. And I'm just trying to remember whether you need to times by lambda or divide by lambda. And I think what you have to do is divide by lambda. So if you think about this, if I just have a think, then the standard normal exponential distribution, rather, I have to stop saying normal. The standard exponential distribution is going to have 1 here, and it's going to go down like that. A general exponential distribution is going to go up to lambda, and it's going to drop much more steeply and go down like that. So it's going to go up to lambda. So what are we going to need to do? We're going to need to divide by lambda, because we want to take if we take a real number over here, let's say this is little x, then we want this little x to come much closer to 0. The reason being that we want the probability of little x to be the that probability. We want that probability to go to a number much closer to 0. So we need to divide x by something to take it. Well, we need to divide it by a number bigger than 1 to take it closer to 0. So we're going to divide by the parameter lambda, and I want to show you that if you do that, this new random variable here, which we could call y, which is the composition of these two maps, firstly map it onto here and then divide every real number by lambda, and let this one inherit the probability space structure of this, i.e. let the probability, well, if we take some outcome s, it will be mapped onto x of s, and this will be mapped onto x of s divided by lambda, and we want the probability density function of this point evaluated at this point to equal the probability density function evaluated at this point, i.e. we want it to inherit the same probability space structure as this one, and therefore have the same sort of probability structure, same space structure as this one down here. So okay, let's work out how y would be distributed. So the way that we can do this is we can ask what is the CDF of this going to be, or we could just go more directly. We could ask, we could ask what the PDF is going to be if we're going to inherit the PDF in exactly the way I told you we were going to inherit it. But it's better to look at the CDF. So we worked out in the previous video that the CDF for a general exponential distribution, sorry, big F of x, was going to be equal to 1 minus e to the negative lambda of x. Okay, so that is equal to the probability that the random variable, let's say, well, I don't want to call it, let's call this random variable u. So the probability that that this random variable u, which is generally exponentially distributed with parameter lambda, is less than or equal to x, is given by the formula 1 minus e to the negative lambda of x. So, if we look at the standard exponential distribution, which was our random variable x up here, then the probability that x is less than or equal to some little x is given by 1 minus e to the negative x, just filling in lambda is equal to 1. Okay, so basically, this is the event. This is asking what is the probability. So if we consider this a probability space with sample space omega prime, event space, set of events curly f prime, and probability measure p prime. This is saying what is the probability of the event of the set that x, the set containing all elements x, such that they are, I should put a different variable u, such that they are less than or equal to x, u is less than or equal to x, and u is an element of the real numbers. And so basically, this is the set containing all real numbers less than or equal to x, and we are asking what is the probability of that in this new space, and I'm telling you that that is given by this formula 1 minus e to the negative x. So basically what I want is, if this probability space is going to inherit the same structure as this, I want the corresponding event, the event in here, so let's just say event e here, which corresponds to this, i.e. if we take its pre-image, if we look at what it was, if we look at what e was under, let's say, x divided by lambda inverse, the inverse map here of this set e needs to be equal to this set over here. So it needs to be equal to the set of real numbers. So u is an element of the real numbers, I think would be a better way of writing this, such that u is less than or equal to x. Okay, so what set is going to correspond to this? Well, when we if we just look at what is this set under this map, then we will find the set that corresponds to, well, the set that has this as its inverse image. So if we just take x lambda, where I'm viewing x lambda as a map of this set u, which is less than, well, u which is the real numbers, such that u is less than or equal to x. If we take the image of that set, then it's going to map every single point in here. It's going to divide it by lambda, so it's going to be the set of real numbers, such that u is less than or equal to x divided by lambda. Because if you imagine taking every real number in here and dividing it by lambda, that's what this is going to, well, it's only going to work if, no, actually that's fine, that is perfectly fine. I was going to say it's only going to work if x is positive, but I think that's fine even if it's negative as well. Yes, that's fine if it's negative as well. If you imagine taking this set, which is all real numbers, so let's say we have some x here, then this set is the set of all real numbers to the left of x, and then if we divide this set, all of the elements here, by lambda, it's going to move this, the maximum value here, to x divided by lambda, so it's going to become all real numbers that are less than or equal to x divided by lambda, basically. Okay, so more paper. So, okay, so that's our set. So we want the probability, we want in this new space, if we look at this new space, and we call this omega double prime, f curly f double prime, and we say that its probability measure is p double prime, we want this new space to inherit the probability space structure of this one back here, basically. So I want to show you the picture. So we want the probability of this set in here to be the same as the probability of this set in here, basically, because we want them to effectively be the same probability space structure. So we want p double prime of u is an element of the real numbers, given that u is less than or equal to x divided by lambda, which we could say is equal to the CDF the CDF of this big random variable y the CDF of y of x divided by lambda to be equal to the probability p prime of the set u is an element u is an element of the real numbers such that u is less than or equal to x, and we already said that this was equal to the CDF of x, the CDF of the random variable x of this value little x, which is equal to 1 minus e to the negative x. So we get that f of y, that the CDF of this new random variable y of x divided by lambda, and that's a little x there, is equal to 1 minus e to the negative x. So now let x equal lambda times, let's say, some little y, and then we can just fill this in. We can say f of this random variable y of lambda little y divided by lambda is equal to 1 minus e to the negative lambda of y, and then we get that the CDF of this random variable y of a little value y is equal to 1 minus e to the negative lambda of y, which is the CDF of a general exponential distribution with parameter lambda. So we therefore get that y is exponentially distributed with parameter lambda. And of course we could then just differentiate this. So if we take f prime of this random variable y of a little y, we get that this is equal to 1 differentiated is just nothing, and then when we differentiate this exponential we get minus lambda e to the negative lambda of y, which gives us lambda e to the negative lambda of y, which is the PDF of the exponential distribution with parameter lambda. So that is standardization of the general exponential distribution, and it means basically that we can think it in the analogous way that we thought of reducing general normal distributions to standard normal distributions. We can think about taking any general exponential distribution and reducing it to a normal exponential distribution.